Okay, thank you so much for joining us for our Go Aero Expert Lecture today. We're so pleased to have all of you here with us. And as always, we're so grateful to our partners and sponsors who are supporting the entire Go Aero Prize, as well as the many organizational partners that we have with us who are joining us from all over the world to share the competition with their communities and advance this technology and innovation that we hope will come out of the competition. We're so pleased to have Chris Speights with us here today. He is the VP of Engineering, Chief Engineer Vertical Lift at Boeing. Chris is responsible for the performance and execution of all engineering activities across the BDS Vertical Lift division, including the AH-64 Apache, CH-47 Chinook, V-2020 Osprey, MH-139 Grey Wolf, and the AH-6 Little Bird. Chris has a diverse background in chief engineering, program management, and engineering functional leadership at Boeing, Lockheed Martin, and Honeywell Aerospace. Prior to joining Boeing in 2024, Chris served as the Director of Integrated Engineering at Sikorsky. He was responsible for the strategy, planning, and execution of aircraft integration, support, modernization, and development. Other key roles included leading Sikorsky Mission Systems, the International Black Hawk as PM and Chief Engineer, and multiple roles at Honeywell Aerospace working on the F-22, B-787, and A350 in both engineering and program management. Chris, thank you so much for joining us here today. We're so pleased and we're looking forward to your presentation.
All right, excellent. Thank you very much. I'm going to go ahead and share my screen. Let me know if it comes across okay.
Yes, thank you.
All right, excellent. All right, good morning, everybody. Thank you for the nice warm welcome. Again, my name is Chris Speights. I'm the VP of Engineering and Chief Engineer for our Vertical Lift division here at Boeing. And this morning, I'd like to take a few minutes and talk about something that's near and dear to my heart, and it's about how we architect our systems considering safety and reliability. And it's not just looking at what our systems can do from a safety and reliability, but actually factoring in those requirements upfront, defining architecture, making design decisions accordingly, and validating that you've met those requirements. So I'm going to talk a little bit about more of the theory and the basics. Hopefully it's not too basic for folks, but it kind of lays a foundation for how you can think about overall systems design to help drive safety and reliability. So the first thing we're going to do is actually talk about a couple of principles here. So I talked about we're going to cover the architecture design aimed at enhancing safety and reliability, but I want to make sure we're clear on a few definitions. So the first thing is, what is the architecture? Sometimes we think about, hey, we're going to go work on the design. And in reality, what we're going to do is work on the architecture first, and then using that architecture, then working on the design. So as you can see here, the architecture would be the structured framework that defines the components, relationships, and the principles that guide the design and the organization of the system. This is one of the most crucial and important phases of the design process, because if you do not select the correct architecture, if you go off and start designing and optimizing the wrong architecture, you're forever going to be in a do loop where you're not able to meet all your requirements or you have a suboptimal design. We're going to talk a little bit about redundancy, and that's simply the inclusion of extra components or systems or subsystems that provide either backup in case of failure, or in some cases it can provide sort of active parallel operation in increasing overall system reliability. And then finally, reliability is really just the probability that a system performs its intended function, whatever that may be. It could be a safety-related function, or it might just be some sort of basic mission or other type of function. We'll talk about a few examples later, but it's the probability that it performs its intended function over some period of time, whether it's by flight hour or some other measurement. So those are some basic definitions just to kind of get us started. I'm going to talk a little bit now about, I touched on it in the intro, but architecture in our product design. There's a lot of requirements that we have when we're designing any variety of products. But I will say safety and product safety, human health safety are some of the most critical ones that we really need to understand upfront. In the aerospace realm, we have to understand, is this a flight or safety critical function? Is it something to do with flight controls? Is it something to do with propulsion lift, right? Very fundamental aviate, navigate, communicate types of capabilities within the cockpit. What is that level of criticality? In some cases, we might define safety as safety to the product. So if you have a very expensive product, even for example, if it's an uninhabited or uncrewed product, you may not be willing to risk the loss of that product. And so product safety itself could be a factor. So is there some threshold that you would define, and any product damage above that threshold would trigger a product safety type of requirement? So when you make sure you understand those safety requirements, the implications, whether it's to human life or whether it's to safety itself, then you can kind of understand what your requirements will be and start defining what your reliability and availability would be. So here you see I want to again stipulate a few definitions, and it's really around what's the reliability or the ability of a system or component to perform its intended function. And we typically, there's a number of terms, but I'm going to focus on what we most typically talk about around mean time between failure. It technically implies that the system or the product is repairable. So you may have a failure, you detect it, and then you repair it, and then you can operate it again. For simplicity's sake, for today, we'll just talk about mean time between failure. Now, the corollary or the inverse of mean time between failure is actually the failure rate. Mean time between failure, if something fails every 100 operating hours, every 1,000, every 10,000, to me, that's a little more kind of understandable. You can kind of like wrap your arms around that one. But when you go to the inverse, it's the failure rate. And so that's the rate that it does not, or the percentage that it does not perform its intended function over a time frame. So if, for example, something is 100,000 hour MTBF, which would be quite high, by the way, that would be a failure rate of 10e to the minus 4. So you can kind of think about that like, the 1 minus that is actually what its availability is, or its ability to operate reliably. If you have 1,000 hour MTBF, 10e to the minus 5, 1 million, or 10 million hour MTBF would be 10 times e to the minus 6. Now, overall, when you have a system composed of multiple components, then you actually have to convert it back and forth a couple of times. But what you want to do is add up all of the failure rates, put that in the denominator, and then that is what allows you to calculate the total MTBF for a system. Now, a couple of core principles on the right side of the slide here. The more complex the system, the lower the MTBF becomes. Complexity is the amount of components, the amount of subsystems, and how they're all connected to each other. But that increased number of components or subsystems increases the likelihood that something is going to fail somewhere within that architecture. So the more complex the system, the lower the MTBF. The lower the part reliability, the lower the MTBF. So if you have a system with 100 components and all of them have lower MTBFs, then of course, on average, you're going to see more frequent failures because you've got 100 parts that all have lower levels of reliability. How can we address that from a system level, though, when we start getting these complex systems? What we really think about are redundancies in order to improve system reliability. And we'll talk about that, and we'll get into some basic math, but a little more math in a few slides. But we really think about redundancies as the ability to increase the system reliability, but understand the trade-off is that you're also increasing the probability of any single failure. If you double the number of components, you're doubling the likelihood that something is going to fail. Now, if one of those failures now has a redundant backup, of course, the overall system performance and the intended function of the system can continue, but you do have more failures that then drive sustainment, repairs, more logistics, et cetera. But that's kind of the basic trade-off that you look at. So that's why we maybe don't want to put redundancies everywhere, only where it's needed. So let's take a little bit of a look at sort of how we arrive at where we want redundancies and maybe where we don't need them. So I actually, the chart on the right, as you might look through it, comes from the Defense Acquisition University, and it really just kind of talks about how you start with requirements, how you allocate those, and how you do some analysis for the ways that you meet your requirements, and how that feeds into a design process where you evaluate potential designs, determine how it accomplishes those functions, and then determine does that indeed meet the requirements. So we talked earlier a little bit about the need for incorporating safety and reliability requirements right up front. So that's part of that requirements analysis block. So in that case, and I'm going to use an automotive example here, but what is the reliability and the safety requirements for a brake system of a car versus the tail light versus the radio? Now, the brake system makes sense. If you cannot brake, if you can't slow down, you have uncontrolled inertia, uncontrolled momentum. Therefore, that can create a safety risk. A tail light, now that signals to somebody behind you that you are going to be slowing down. Safety? Yeah, I think so, but it may not be an immediate hazard, as in you are going to crash and there's for sure going to be damage or injury or harm to the occupants. But it could be maybe a little less likely if the taillight goes out and somebody's following too closely and the weather is bad. There may need to be multiple things that happen until that creates a safety risk. So maybe the reliability doesn't need to be quite as high as the brake system, but it still can be important. Now, versus a radio, what kind of safety or reliability requirements would you have for the radio in a car? If the radio fails, is it going to be an immediate safety issue? Probably not. Now, that assumes that it fails off. What if it fails by going to maximum volume and you're unable to manage it and control it and it becomes a big distraction? That could be. The likelihood of that happening is probably low. You could do the analysis and understand if you need to allocate some sort of safety requirements to the radio that would require some sort of backup, some sort of, hard button that disconnects the radio and stops it from playing. That's the way that you would kind of look at requirements and the likelihood, doing functional analysis and then looking at your design. The reality is that the incidence of a radio going to maximum volume and being unable to turn it off is probably so remote as to not be driving the requirement. It doesn't need to drive the design architecture and the requirements. But the brake system, if it does fail, even if it's remote, that is so critical and so important that may absolutely drive safety requirements in your system. So, kind of looking at the second major bullet here, that discussion kind of leads you to understand that depending on what the functional needs are, what the intended function of the system or the component, you can determine if maybe a single thread is acceptable, or if you need to have some level of redundancies, either backup or parallel operation. And again, using the brake system as an example, if the failure to perform that function is unacceptable, then you should consider levels of redundancy and understand what the resulting system reliability and failure rates would be, but making sure that you have that level of redundancy into the design from the beginning. If you're not familiar, most automotive brake systems do have levels of redundancy. At a minimum, you have an emergency brake, right, with a physical cable. Sometimes it's an electrical cable, but it's in a separate circuit that activates a separate mechanical braking mechanism in parallel to the hydraulic system. And many times on the hydraulic systems, you might have parallel master cylinders coming off of a single brake pedal, because the brake pedal might be deemed very reliable, but the two master cylinders, maybe one of them can have a leak. So you kind of look at where that level of redundancy is. And then at the higher level, again, you might have an emergency brake as the higher order level of redundancy for a system that's critical and failure would be unacceptable. Okay, so that kind of talks a little bit about how we determine and understand the requirements, the level of criticality from a system perspective, and a little bit of the design process where we go from requirements to functional allocations and then evaluate the design and feed it back. Going to talk a little bit first about single thread failure modes. And, very simplistically, when you have a sequence of events, a sequence of components, and, for example, in the case of a chain, in this case, you've got 4, 8, 9 components all in series. And if any one of those fail, then the system fails, right? So that's very clearly the representation for single thread, and that whatever the lowest MTBF or the highest failure rate component is, that will end up driving the overall system failure rate. There's some math associated with that you can look at, but the actual driver will absolutely be that lowest MTBF component. And the overall MTBF and failure rate will be closer to that one than the best one for sure. Some simple examples of this might be a single engine airplane. So, right, for anybody that maybe looks at, what's going on in general aviation and with Cessnas, and I see videos all the time of a engine out and what did the pilot do? They're gliding, they're doing, different things, calling for Mayday, looking for landing zones, etc. And of course, the answer to that was very early in aviation to have multiple engines. And if one engine goes out, the other engine can still cruise and help you land. Now, of course, if you kind of understand the requirements, you probably cannot take off with a single engine because you may not have enough power or thrust and it's asymmetric and there's a lot of forces at play there. But if you are flying and then one engine does fail, then you can continue to fly and land and, with various levels of emergency procedures with your remaining engine. And then of course, if you look at large commercial aircraft that fly transatlantic, transocean routes, for many years, the move was moving up towards 3 and then even 4 engines to provide levels of redundancy so that you did not need to divert to other airports. You didn't need to divert your overall route and your flight plan. But as engines and designs have become more reliable, as we've put in improved contingency management, we actually have ways to certify extended twin engine operation, which is extended single engine out operation over oceans. So as design systems and technology improve, our ability to deal with redundancies improve because if you think about it, 4 engines, you're going to have twice the number of failures as a 2-engine aircraft. And increased sustainment and other sort of logistic burdens. So those are the sort of considerations that go into whether you have single thread and what you do for parallel operation. Now, just as a little example, I put here, you might have dual engines, for example, on an aircraft, but if you have a common fuel system, you still may be single thread somewhere. So you actually have to think about, you may be single thread in some areas, and then you can go to parallel, but it still may come back to single thread. And part of the focus in architecture and design is to really understand where those single threads are, where you should drive parallel capability within an architecture, and where it is okay to have single thread. So I gave the brake pedal example earlier. We do not have 2 brake pedals in a car, one for backup. We have a single brake pedal because the reliability and the failure rate is so good, or failure rate is low, the reliability is so good that you don't need to have multiple brake pedals. So those are some of the design decisions that you make, understanding what the common mode failures or common single thread failures might be, even for systems with levels of redundancy. So I guess the real takeaway here for single thread types of discussions is you need to understand how the different subsystems interact that either provide true redundancy, or are there common modes or other common single threads up and downstream, and just make sure that you understand that it's intentional, and that it, by the time you do the math, that it meets the design function for that system or subsystem. Okay, so I'm going to pivot a little bit now to talk about parallel levels of redundancy. 2 kind of broad categories to think about in levels of redundancy. The first is active redundancy. This one's a little interesting, and we use this in aerospace quite often, where components operate simultaneously. This is not one is operating and one's in standby, but rather 2 are constantly operating. One example I talked about already was a dual engine aircraft. Another example in the flight control space, another control system space, is where you might have combining or voting logic, where you have multiple decision-making controllers that are evaluating what the action should be and either averaging their view or maybe voting to determine which one is right. Now, here's the trick. If you only have two units and they're both voting and something is wrong, how do you know which one is wrong? So for very high reliability and safety critical systems, sometimes what you'll see is actually triplex redundancy. And you'll see three votes and you discard the non-conforming vote. And typically, hopefully, most of the time, all three are voting the same, and you just default to one as the primary. That as long as all votes are within parameters, then you just look at box A. But if one of box A, B, or C is different, then you discard that and then you use the remaining two votes. And you can either average them or you could pick one primary and then one more backup. But whenever you get to two systems in an active redundancy or two components in an active redundancy sort of architecture, you have to really be careful that do you know which one is right and which one is wrong, or do you just know they're different? That's one of the biggest challenges that you have in the system. We're going to talk a little bit more about that in a minute. The other one, which is probably a little more common and people might be more familiar with options and architectures around that, is really a standby redundancy, where you have an active and something in standby, backup components that operate upon failure. You might have a primary electrical system that could go to a backup bus. It could be an AC bus that has a DC low voltage backup. One simple example is you might have primary GPS, but in an aircraft, and the GPS will have levels of redundancy and different sensors and parallel systems in and of itself. But if for some example GPS just didn't work, the satellite system was denied, there was a massive solar flare storm, whatever it may be, then the level of redundancy actually ultimately is going to be a magnetic compass and a map. And so the pilots will always have some form of a backup indicator that helps them navigate even if they lose GPS. So this would be kind of layers of redundancy within the system. But again, much as with active redundancy, the detection of a failure and being able to gracefully transition from a primary to a backup are very important factors in your architecture. You can't just say, well, box A was telling me to go full right, but it turns out that was wrong and box B wants to go full left. You need to have a way to gracefully transition between those through algorithm logic and other can be mechanical means also. So those are a couple things to think about on parallel redundancy. I'm going to give a little math summary just so we can kind of have in mind what some of these numbers might mean. And this is a real basic system. I hope none of you are designing systems with only three components. I doubt that's the case, but it could be three major subsystems that boil down to this type of reliability, and you have three subsystems that accomplish a function for a vehicle or any type of product. But really, when we look at the reliability of a system, the math is quite simple. The reliability of the system is simply the product of the reliability of all the components. So in this case, if you have three components that are all 99.9% reliable, right? They only fail 0.1% of the time. Seems pretty good. It's actually not that great for aerospace, but in general, seems pretty good. Your overall system is going to end up at 99.7% reliability. The system fails 0.3% of the time. Sort of makes sense, right? Three components, more than one, fails three times as much. Math works in this case. Now for parallel systems, it's a little bit of a different. You have to do a couple of transformations first. You actually want to do what you want to do is multiply the unreliability of the components and then subtract that from one to get back to the reliability. So when you look at the parallel system reliability and the equation here, 1 minus R1 is the unreliability of the very first component, and then you multiply that by the unreliability of the second component, and so on. After you get that product, you then subtract that from one. So in this case, if you have three products that each have 99.9% reliability, and I put the zero there as a significant value to make sure you understand that's not a continuing string of nines. So then the math works that, if something is 99.90% reliable, you look at the unreliability of each one, which is 0.001, you multiply that out and subtract that from one. That gets you 1 minus 1e to the minus 9, or 99.9999999, as it turns out, percent reliability. So in the other case, when we put the three components in series, it went down to 99.7. When we put three components in parallel, it goes up to 10 times e to the minus 8 or 1 e to the minus 9 So the impact of paralleling components can be pretty significant. And in fact, I talked about very flight critical systems that get triplex. This is exactly why. And you could go do some of the math yourself and kind of play around with the numbers to see how dual redundancy or triplex kind of influences the overall reliability and the outcome of the system. But there is a catch. We're going to talk about these these primary and backup modes, the parallel math counts when a failure is detectable or known. It absolutely can exponentially increase the reliability of safety-related systems. Like, I talked about flight controls as a classic one where we would, for fly-by-wire systems, would typically have triplex systems. Duplex can meet the requirements in some cases, but triplex just gives you that highest level of system reliability. But an undetected fault, like I've talked about a little bit, if you don't know if your primary or your backup is the correct one, if you don't know for sure in an active parallel system, which one is the one that you should be believing and which one should you discard, then the math starts, the simple math I showed you starts to fall apart and you can start fooling yourself. So what's really critical from an architecture standpoint is instrumenting the architecture in some meaningful way. Real-time diagnostics and sensing becomes the most critical factor to realizing the backup architecture benefits. You need to know if something is operating within parameters and is giving you good data, or if something is bad and you should discard it and go to your backup or stick with your primary, depending on the case. That's really, really important. One little side note is you can, in many cases, maybe think about virtual sensors that can validate. Are there other data sets that you can pull together and be able to compare to determine, is this valid data, not just with direct measurement, but with the inference from multiple other pieces of data? But now if you believe and understand that sensing the function can be important in order to be able to account for the reliability and the failure modes, it actually raises another question. What if the sensor fails, and do you need levels of redundancy in your sensors? And then, is that duplex or triplex? And then how do you know those sensors are within parameters? And do you need sensors for the sensors? It can quickly kind of go down a lot of different rabbit holes, which creates a lot of challenging complexity, which is exactly why developing the architecture and identifying the needs and the ability to meet some of those system safety and reliability requirements can be so critical, and it's not so easy. All right, I'm going to just talk about a few more things, and then we're going to get to Q&A here shortly. I've kind of hit on this a little bit, but one of the key things that you want to think about are kind of like the levels of protection that you can provide. And I know it's not engineering, but it just struck me as I was kind of looking at, thinking about layers of protection. The CDC, the Center for Disease Control, actually has some interesting things that I think are applicable here. And I kind of wanted to draw a parallel here. The CDC says the absolute best way to eliminate or reduce a risk or improve reliability is actually just to eliminate the hazard itself. You can substitute, you can have engineering design, I'm going to call that architecture, you can have administrative process types of controls, and then the very final hierarchy of control, the last or the least effective and the last one that you want to have to use is personal protective equipment, goggles, masks, etc. But if you can eliminate the hazard in the very first place, then that's actually the best approach. So when I look at it on the left side and in terms of our design, I think about, hey, can you simplify the design? Instead of optimizing a part, can you eliminate a part? Do you really need all of those parts? The simpler it is, the more reliable the system will become. Substitution is picking high reliability components, making sure you understand what you need to actually procure. If you're building something that goes into space and a human hand is never going to touch it, right? A satellite or something similar, an unmanned satellite or other type of a vehicle, then you probably need the absolute highest reliability component possible. If you have something that's very easy to maintain and support and it's cheap and easy, then you don't have to pick the $1 million transistor. Then after you pick your components, now you want to understand, based on the reliability and their ability to meet the requirements and the safety requirements, what levels of redundancies in the architecture do you need to include? So we've already talked about single thread, parallel, active, passive sort of backups. But that's under that engineering control side, along with monitoring real-time diagnostics so that you actually get the value out of those parallel systems. You could also use some prognostics and health management that's maybe not real time, but you can come back and look at trends in data and understand what's going on and be able to help drive reliability by preventative maintenance and bringing things out before they actually fail, but getting indications of the failure. And then the very last one would be, safety protocols, procedure management, emergency procedures, contingency management. And then I was thinking in the realm of PPE in aviation, if it's a human flying an airplane, the last line of defense is maybe going to be a parachute. And then I'm thinking, right, well, it's not just for humans, it's also for aircraft. So when we think about layers of protection, you might want to say like, hey, there's a multifunctional level of redundancy that you can apply. And when you think about like a parachute on a Cirrus aircraft, that is really a level of redundancy for the wings, for the propulsion, for the controls, for the navigation, for electrical systems. So this becomes a parallel system for many, many of the subsystems that you could look at. Now, there's still, I don't think I'd want to land in a unguided parachute aircraft. I think they still come in pretty hard. I was telling somebody, I think it's more like a 40-mile-an-hour car crash versus a 200-mile-an-hour car crash. So it's much better, but still undesired. So you'd rather do it with architectures and other things before you have to deploy that last line of layered defense, your personal protective equipment or your plane protective equipment. Okay, so just a couple more to wrap up and we'll get to Q&A shortly. So watch areas when you're defining architecture. The first thing I will just emphasize over and over is adding redundancy everywhere can create complexity. You need to allow the math and the requirements to guide your design. Don't just add redundancy because, hey, more is better. You do it in the right places and where it's needed and where you understand it drives system safety, product safety, et cetera. The fault and failure detection is so critical. I've hit on that 2 or 3 times, but you will not get the full value of backup systems or contingency procedures if you are unable to detect the fault or failure. And believe me, faults and failures are not always so clear cut. It's not like, hey, this was working and now it doesn't turn on. The absolute worst thing that can happen is when you think something is working, but it's giving you erroneous data. And understanding that erroneous data and understand that that's what it's giving you is the most critical aspect to being able to leverage, the levels of redundancy. Now, we talked about increasing redundancy not only drives complexity, but it does improve system reliability at the system level, but it also increases the frequency for failures, increases your sustainment and maintenance logistics, and overall, drives complexity throughout the entire chain, not just the product design itself. And then the other thing I would say is, don't design for something to be 10 times e to the minus 9 when e to the minus 5 or even to the minus 3 might be perfectly acceptable, depending on the function and also the contingency options. What happens if it fails? Understanding that is how you set the right requirements, how you help drive your architecture, and then that ultimately gives you the optimal design. So, a couple of final thoughts. Hopefully one of the things that you take away here is you absolutely need to think about safety when defining the architecture. Do not do it after the fact and say, oh, here's my design. I wonder how safe it is. I wonder how it'll operate. I wonder how reliable it is. It has to be factored in upfront, and you really need to, that'll help demonstrate an understanding of the mission needs, of the product needs, and then help you understand what the right architecture is going to be. Understanding the function of the system and the components within the system is important to understanding what their impact on safety and overall system function is. You need to define and decompose the functional needs into reliability and failure rate allocations. So if something cannot fail, like our brake system example earlier, you need to make sure you decompose a very high reliability for that system. If something like the radio knob can fail or whatever, some more non-consequential function on your platform is, then you can allocate it a little bit higher failure rate. That way you don't drive a level of redundancy, complexity, cost, weight, and all of those things that go along with it. So the right allocation to the right component is how you optimize the overall design. And then once you understand those requirements, that allows you to choose your components and architectures to meet those requirements. And then I threw in on the right side, validation is there's always, if you validate your design and you find some gaps, you can always feed it back up to the top on your requirements and your architecture. So there's always a design process that's continuous. It's not just a single flow. Okay. And then my last guide for all of you is if in doubt, keep it simple. Low complexity, simple systems, I think typically wins the day, and that's what I'm really in favor of. And it helps us be able to meet those really challenging requirements for balancing not only just safety, quality, functional, operational requirements, but really helps you come up with an overall optimal, beautiful design. So with that, I think we are done, and we will pivot over to Q&A.
Yeah. Chris, amazing presentation. Thank you so much. A lot of information here, folks. Remember that the lecture is being recorded and will be posted on HeroX. Should you would like to go back and reference the math that Chris has talked about as well, and see if there's anything that you'd like to review. We have a couple questions that have come in already. So folks, please continue to use the Q&A button at the bottom of your Zoom bar to continue to post questions. Chris, a question we have is great presentation, really enjoyed. How can new technologies like AI, machine learning, et cetera, optimize architecture design? Where can future innovations go?
Yeah, it's a very profound question with a lot of layers. I'm gonna say real simplistically, right? So if we think about what AI machine learning does, it's a little more than this, but I'm going to simplify it to, it's a statistical machine that looks at training data and assumes that that training data is correct and optimal and able to inform future decisions. So you need to be careful with how that data is trained and what it's telling you, or else you might be sort of on a path to just doing things how they've always been done. Now, if you take the data in a way, in the tools in a way that helps expand the envelope and explore new architectures, new design principles, then I think that's where the real promise is. You just have to be sure that it's not kind of guiding you back to how we've always done things, but really identifying ways to optimize your designs in the future. So with that being said, I think that architecturally, there's a lot of interest, opportunity for Gen AI, machine learning to be able to come up with some novel solutions to things that maybe, to approaches that maybe we haven't thought about in the past. I do worry that sometimes it might be overly complex, and knowing that my principle would be keep it simple. You need to make sure you're not coming up with an overly complex answer, but being able to use those tools to do trade studies, come up with performance trades to see what combination of subsystems is going to be able to best meet your requirements. The permutations is almost uncountable. And so leveraging those tools to help narrow down architecture sort of categories, narrow down some of the options, and come up with some ideas that maybe you wouldn't have just naturally thought of, I think can be really good. But I really think of AI as partnering with the experts. You cannot just go in, utilize the tool, utilize a Gen AI tool to come up with architecture or design, and not be able to shape it, prompt it, adapt it based on your subject matter expertise. So I'm a strong believer that you need to have you need to personally, the human needs to be rooted in fundamentals and first principles in order to best leverage those tools. But the tools absolutely can give you some rapid iterations, rapid simulations, and perhaps even define some architectures and designs that were not immediately obvious, but hopefully simple in ways that help really meet the overall needs of a system. The last one I'll say, just very tactically speaking, Gen AI just needs to have algorithms and equations and relationships defined. So if you set up a framework where you can define things like what your requirements are to the types of functional architectures that can achieve those requirements, you need to have a model-based systems engineering approach in order to be able to help feed that into some of these types of tools. Building things indoors and textual or database is going to be difficult. So I think pivoting towards more of a digital thread, model-based systems engineering, and having functional architectures that can be validated against the requirements is going to be necessary in order to really maximize the use of some of the Gen AI tools. I don't think we're using it enough. I think there's a lot more opportunity, but as I said, make sure that you're not just training it with old data and you're getting the same old results. You need to have subject matter experts that are partnering with the AI tools to help guide it through the process. And then, I think there is some opportunity so long as you're leveraging a digital thread model-based systems engineering environment. All right, that was a lot for that one. Hopefully that was okay.
Great, thank you. Using design assurance methods, we can meet required levels of safety, but our assumptions about operators' ability to detect and respond correctly, even when they are properly trained, may result in higher than expected accident rates.
Yeah.
How do we address the operator aspects when designing for safety?
Yeah, I am such a huge advocate about human factors engineering. So understanding the human part of the equation, and it's not just, hey, here's an emergency button, but is that button, able to be seen, used, leveraged, understood, not misinterpreted, not, we didn't hit the wrong button, we didn't accidentally hit it. Understanding the human factor side is so critical to defining requirements. Um, I didn't really hit on that from a safety perspective, but the human side is so critical. So what I would say is leveraging human studies, right? Videoing, watching that it's actually an opportunity for Gen AI, to be able to process video of humans interacting with whatever the product is, whether it's an aircraft or ground equipment or some other type of vehicle or any product really, and being able to monitor and understand what are their tendencies, where do their eyes go, right? I'm a huge fan of eye tracking to kind of understand what the workload is on the operator, and being able to translate that back into performance, sort of performance algorithms of, hey, here's the percentage of time that the person is able to review this or look at this, or here's how much time it takes to evaluate some data and take an action, and then using that to inform your requirements and then inform your design itself. So I would say a as deep of as an understanding of the human machine interface, understanding how that drives the actual use of some of your design features that you intend, and then using that data to help drive back to requirements that help you shape it in a way that's meaningful. And I'll say, in the aviation space, especially, we're significantly focused on workload. We cannot just overload the pilots in an aircraft, whether they're in the aircraft, they're on the ground, wherever they are, the operators. You cannot just overload them with data and information and expect everything's going to go perfect. So if you have a 1,000-point checklist that a human has to do, then you haven't done your job. You need to automate things. You need to simplify. You need to understand what the capacity and workload, the workload capacity is, and then help define your design and architecture around that. And then when you talk about the design assurance methods, I would just say that's absolutely what drives into your DAO level assignments when you're parsing out safety level requirements and allocating functions and safety to your systems. Okay.
Thank you. Let's see. What do you think of reliability of distributed propulsion VTOL aircrafts,
Oh,
as they are claimed to be more redundant without any single point of failure?
yeah, great question. I love that one. I think there is a lot of promise in it, but there was probably some early learnings from common mode failures. And I touched on it just a little bit, but systems that are independent and isolated can fully accomplish the level of parallel operation that you're intending to give the reliability. So early on, there was a few examples of where aircraft broke a prop rotor, and that prop rotor then was expelled into the neighboring prop rotor, which then caused a cascading failure. So an understanding of the cascading failure modes is critical, and then designing things in a way that they are less likely to cascade, and then even testing them. So real simplistically, you need to put a cascading failure requirement into the upfront design, and then you can evaluate your architecture and your layout against that type of failure. I think everybody kind of learned from a couple of those lessons. Really interestingly enough, it was great. I think Joby had one aircraft that was crashed. It was being flown autonomously as a part of a flight test and, envelope expansion. And it was to me, it was actually a good success story because they had a critical learning without risk to human life. They knew that there was risk, therefore they're flying them remotely piloted, and they were able to understand what happened with a cascading failure and able to address it to improve that system reliability, decrease the probability of cascading failures, and thereby overall improve the reliability. So I think distributed electric propulsion, or even, it's really just another version of distributed propulsion that was used starting from the very early days of aerospace. And I think that there's a lot of diligent thought looking in, that's going into how to have distributed energy storage, distributed energy transmission, and ultimately distributed energy conversion to propulsion. And I think that's going to offer some solid benefits because the reliability in those systems has to be 10 to the minus 9. There is no room for any high level of failure rates in that eVTOL market. So, okay, hopefully that helps.
Thank you.
I think I hit it.
Yeah. If there are more questions, please feel free to post. I just wonder in the meantime, Chris, if you can speak to a little bit more about, the teams are currently working on their aircraft.
Yeah.
They've just finished stage 2, and now they're going into the next sort of probably year and a half or so until, first quarter 2027, where they're building their full-size aircraft for the final fly-off. And I just wonder if there's some certain aspects of sort of the architecture that you're speaking of in terms of the design and the full build out that they're now going to do at full scale, particularly when you think about an emergency response flyer,
Yeah.
certain aspects that they might consider or that they should think about.
Yeah, I would say try to simplify the systems in a way that you can evaluate what your reliability to both perform the mission is and to perform flight safety. And then I think probably one of the most critical things is safety to ground personnel. So in a real scenario, if we're having unmanned vehicles perform emergency management functions out there, the last thing you want is to create an added risk. So understanding what your overall system reliability and what your contingency modes are, right? Is there if loss of GPS, does it go into a hold pattern? What types of requirements do you want to define for these things? Do you have denied GPS navigation capabilities? I would lump those, try not to get caught into the weeds of doing reliability analysis at every little component, but try to bring it up at the subsystem level and then use that to help understand, do you need contingency managements? Do you need levels of redundancy based on the failure modes of those subsystems? I think if you go too far down into the subsystem analysis, you might get lost in the weeds. You might get lost in the sauce. So making sure you keep it at a high enough level so that within the time allotted of the competition and your efforts, you can have something meaningful. I think that's going to be the most important aspect. If you go down too far in the weeds, you might get a really good analysis on your propulsion system, your navigation system, but that's only going to be part of the story. So, making sure that you demonstrate an understanding of what the product safety requirements are, what the availability reliability is, and it's not just the ability to perform the mission, but it's the ability to not endanger any ground personnel or anybody else. If you can touch on those points, then I think that'll demonstrate that you're on your way with a good architecture and a good understanding of the design and the requirements.
Hmm. A really interesting perspective there. Another question is, do you use STAMP, the acronym based on the three basic concepts: safety constraints, hierarchical safety control structure, and process model? Is it useful to you?
So you have quickly exceeded my area of expertise. I'm already stretching in the R&M folks, and I'll have to say, right, at full admission, right, we've got some really great folks within Boeing that are just dedicated in our reliability and maintainability areas and with our system safety teams. So I'm going to say that question is a little beyond my side. It's something we could maybe follow up afterwards on. The place that I've really, from my role as chief engineer of vertical lift, I've really been focused more on how we integrate our different architectures to meet the high level system requirements and understanding how we optimize designs to meet those mission requirements from the customer.
Mhm.
Uh, I'm not familiar with stamps, so I'm going to have to take a rain check on that and be able to see if we can get some feedback afterwards from some of my subject matter experts.
Of course, thank you.
Yeah. Which I'll say, by the way, it's the beautiful thing about, leading teams and things. It is impossible for you to know as much as your whole team.
Mhm.
So leverage your team. Don't try to do everything yourself. Don't try to know everything, because if you do, it's a lost cause. The best thing you can do is build great teams with people that really understand it. And undoubtedly, I'm sure that there's folks on the team that would have knocked that answer out of the park, but they're not sitting in this chair at the moment. But that's okay. I know what I know and I know what I don't, and I like to stick to my lanes.
Of course, and you
Good
know quite
lesson
a bit.
there.
So right, absolutely. If there are any final questions, please feel free to use the Q&A. Chris, thank you so much for your
Yeah.
presentation. As a reminder, teams, the lecture will be posted on HeroX and will be available to you for reference. Should you have additional questions, please feel free to reach out to us at info@goaeroprize.com. As you all know, we've just finished stage 2. We are now beginning the process of registering additional teams if you would like to join for stage 3. More lectures are forthcoming, as well as continued opportunities for mentorship and support. So please make sure that you are paying attention to herox.com/goaero for all of those announcements and information. Chris, again, thank you so much for your time. Very much appreciated. And we look forward to sharing more about the teams and as they progress with you.
Excellent. Thank you so much. Appreciate you having me on, and yeah, good luck to everybody.
Take care.
All right. Bye-bye.